least.
Okay, so let me get started. So first of all, let me thank Vilsna for inviting me. We go back almost 10 years when we met Petroleum Institute, and had a quite enjoyable time of working there, despite the heat. So we started collaborating, and then it has been continued. Just has been to Stockholm also, and we recently finished also a paper together. So hopefully this will continue, and I'm sure it will. So thanks again. I look forward to see you around in Malmö as well, besides doing some work. So I'm going to give a series of lectures about free boundary problems. And so the term free boundary problem has, of course, backbones that I will explain. But always you can think of a partial differential equation. And since the backbone here is a little bit different, so I'm trying to do, so my slides will be a little bit advanced in the sense that there are not much that is said in the slides unless you're familiar with the topic, at least with advanced PDE. So what I'm going to do is I'm going to run a parallel slide here on the whiteboard, and then we have a little bit more details that Josna will take up later. And during the course of the talk, I will also present some questions. So you can see like there are going to be a lot of things that are a little bit vague, or you have a lot of vague sometimes, and in between the lines we have to fill in, and that we will do maybe in the afternoons, etc. So that's going to be how it works today, or the rest of the week. So let me start with a few homemade videos. I don't have my glasses, I have to see which one I want to pick up first. So there are 3 videos that we did at home. My daughter helped me, and this was actually for a talk I gave in July in Shanghai about free boundary problems, and the conference was about free boundary. So let's see if this is going to work, and apparently it doesn't, as it is always. Oh. Okay. Okay, so it works. If I yeah, it's okay. That will be okay, yeah. This is enough, yeah. So well-posed problem, you can actually solve it mathematically, that model. You can model it and solve it, and we're going to actually model this very soon. And then the next one, when you're separating the plate, this is not well posed, and so you don't say every time you push it, the same picture you push it, you get the same picture. That's a round shape eventually, but the whole continuous process is always going to be the same. But when you're separating it, every time you do it, it's going to be a different picture. So it's ill-posed. So you don't get the same answer. So mathematically, you don't have a solution to this problem in general. So that's a huge problem in oil industry, actually. Because in oil industry, what you do is actually you're separating the plates. But it's done differently. It's not like separating plates. There are a lot of wells that you're sort of sucking the oil, trying to suck the oil. But that comes with pressure of water that you have from the ground, and that water can make fingerings. So it makes a finger, the water goes all the way to this well here, and then water comes out instead of oil that you're looking for. So that's a huge problem actually in oil industry. So solving that problem is mathematically very hard. So this is one picture I had for you, and hopefully the next one. Close this. So this one is something similar, but it is two-phase problem. So these are the same shampoo, so this is mathematically incorrect, but same shampoos, I just color it differently so you can see the difference. And when you push it, you see that there is a very nice interface, and there is also a little bit of mushy region actually that happens. You can think of water and ice also, and then there's always in between a region which is neither water nor ice, so it's called meshy region, the meshy region. And this is also a free boundary. You don't know where it happens when you start the process, and it evolves during the time of your process. Okay, the third one is this one. So I just took the old one with a lot of water in it and then put another clay. And what I'm trying to do is trying to reach this edge here, the corner. You see, I'm pushing and pushing, sort of I'm not getting there. You see, I'm pushing and pushing. Of course, this is not exact, and it's not continuous, but if you would do it continuously and exactly, the question would be for you, can I reach that edge? So you start with water here, liquid, and then you pour the liquid continuously, okay? And then the question is whether you can reach this point or not, because the water runs over the table here. And then the question is, can you really wet this point? Think about it. Well, it has to do with the corner. If the corner is too small, you will not reach there. This is related to somehow to Brownian motion, if you're familiar with stochastics, that starting walk from here, possibilities of reaching here before here is much more that you reach here. If the corner is smaller, you will have problem getting to that corner. And smaller corner means that it takes much longer time. And actually, when it is less than 90 degrees, it takes forever. If it's larger than 90 degrees, you can reach that point. If it's less than 90, you will never reach that point. And this, again, is a very important aspect in industrial processes when you're filling with mold filling. You're filling inside and you want to reach the corners, but you don't see that because it's inside and you have this figures you want to fill in with the materials. But if you have corners, mathematically you realize you will never reach that corner, and that corner actually you will break. This example you can see specifically with your eyes if you walk to SBC building. Is it SBC? the web place I'm staying is now CBS or maybe
CBS.
CBS building, and you will see that the place you're walking, the tiles you're walking in the front gate, is broken. The reason for that is broken because they were filling it inside, and they never reached that corner, and that corner is exactly 90 degrees. And I was actually seeing that exactly that they didn't think about this. They should have asked me before. I would tell them you will not reach there. Anyway, I'm joking, but okay, so this was the fun part. And what I'm going to do, I'm going to try to develop, I don't think my glasses, I realize, I'm going to develop a complete theory, not only around this problem, but around a bunch of problems. And the theory, I will start with a little bit of modeling. So today will be mostly modeling. We will see different problems. I think we have 6, 7 different problems. And the modeling would be at the level of hand waving, because we will not be able to go into the details of the modeling. And from tomorrow, we will do the mathematical parts. But also today, you will see a lot of mathematics that might be quite new to you. Okay. Okay. Okay, today will be mostly about a catalog of problems that are related to what we call obstacle problems. So obstacle problems are problems when you have, so do we know the Dirichlet problem generally? So you want to solve the heat equation, let's say, the Laplace equation in a domain. Most of us have been probably doing it in a course in Fourier transform or something like that course that you solve the Dirichlet problem. And when solving the Dirichlet problem for specific domains, it's not so hard, like a disk or a rectangle. And then you go on and you want to solve it very generally. And you will see that today we not only solving that, but we're solving similar type of problems, but in a domain which is unknown. So you don't have the domain. So that makes the extra pressure on you. So let's start with the Dirichlet problem. So you start with a ball of radius r, and the voice is gone. You start with a ball of radius r. The battery died. And this is of no use, but so you have a ball of radius r in the center of origin. Laplacian of u is 1. So, and you want to solve this problem with bounded alpha 0. So Laplacian, let me just remind you, if I'm not doing it already here. Yeah, I'm doing it already here. So this is the Laplacian. That's the summation of the pure second derivatives. And then you want to solve this problem. This you should be able to do by hand. Okay. The reason for that is that you're working in a bowl, and Laplacian is spherical symmetric, so you can change the operator. If you make a rotation, it doesn't happen anything to it. It's isotropic. Okay. And that means that the solutions are going to be isotropic. And that means that you can actually consider just one-dimensional problem. But in this case, it's even easier because if you just make a correct guess, then you're done. And the guess would be, of course, this is the solution. Because what is the Laplacian of a function which is 1, you can always think of x squared, the Laplacian is always 1. You just have to divide by something that makes it 1. And then divide by this, the dimension dependent constant. And then this function is not 0 on the boundary, so make it 0, because on the boundary it's a ball, it's going to be exactly constant, and that constant is going to be r squared and 2n, so you just subtract it. That's it, then you have the solution. So you either guess it, or you really sit down and solve it. If you have experiences, you know it's rotation free, you can rotate it, and nothing happens with the Laplacian, and you can just take a function which is like x, absolute value of x. This is the solution, and this you could do already in your calculus 2 course. But now I'm adding one extra parameter to this. I'm saying, okay, I want my solution also have, let's say, one of this, that the total mass of my experiment, whatever it is, u, the total mass of should be lambda 1, so the whole interval is lambda 1, or that the gradient, so the norm of the gradient should be a given constant, lambda 2, on the boundary. Then you see that this problem is not solvable, because R is already given to you, the domain is given to you, and you will compute the gradient, and the gradient will come up naturally from your exact function. And it's not necessarily going to be the lambda 2 you're giving. So this means that, okay, I cannot solve this problem. But if you want to solve this problem also with this lambda 2, then what you do, you say, okay, we let R to be free. So can we find a domain where I can really solve the Dirichlet problem, and in addition also have this extra boundary condition? Okay, so what you do, you let the domain here, let the domain be free. It means that you have to let R to be free. If R is free, then it will give you a different gradient on the boundary, depending on what R is, and then you will eventually hit this lambda that you were looking for. And that gives you your solution.
And he said he will replace.
Yes,
But it is getting recorded. So
oh, it's getting recorded?
Yeah, it's getting recorded, so it's fine.
I don't need.
No, you don't need to wear it.
Okay, I don't need to wear it.
It's still getting recorded.
Okay. So this means that you eventually solve the problem by letting R to be a free parameter, because that lambda might be very important in your problem. And actually, many problems in nature are of the kind when you really don't know the domain, but you know the information about this boundary condition, extra boundary condition. That gives you, we will come to those problems as well. And that gives you actually a freedom of letting R to be free and find the solution. This is a very specific spherical symmetry, very similar, almost is one-dimensional, because in Rn, when you have spherical symmetry, it's a one-dimensional problem. Okay, so let me go on. So the term free boundary is actually related to exactly the fact that you're letting the domain be free. And the problem is generally overdetermined, and you cannot solve it in general, and in some cases you do solve it. So here is a picture for you, and it borrows from the World Wide Web. So you think of a big piece of ice blocks, and with or without penguins there, and then this ice block is melting, which is actually happening nowadays in the world. It's a curse now. So the frontier of the ice, the shape of the ice is changing. And you don't know how it changed. Next time you don't know. This again is a non-deterministic problem. It happens, I don't know where you can do that, and you have to see in the future. And actually, you turn this problem into a deterministic one, and you can actually exactly solve it and see predict the future if all data is given to you. If all data is given to you, you know that this ice block will have this shape at time t. But then you need all data. If there's no other things that surprising you, and you will have the exact shape. And that's by solving a sort of heat equation. And you realize that ice itself is cold. It's not zero temperature. It has a temperature of -10 maybe. And that means that inside the ice, it's not only -10, it will be -10 here, it will be -5 somewhere else, and at the front it will be almost zero. And it means that there is another heat equation in the ice. You're not used to thinking about heat equation with cold places. But cold places do have heat equation as well, because there is a temperature. Temperature is just negative. The heat equation has the function u, the caloric function u, has actually negative values. It means you have a heat equation in the ice, you have a heat equation in the water, and then there's a balance. And then you have a function u, which presents this heat equation. And this function u is sort of zero exactly in the boundary. If we assume zero is exactly the time, the value for the heat to be neither water nor ice. There's a mushy region around it, so you consider it as a smooth boundary. And that boundary, so you have heat equation, the function u here solves the PD, There might be impurities in the water or in the ice, then the heat equation is not heat equation anymore. It's a sort of different type of equation, but very close to the heat equation. It has other parameters in it, because there are impurities. What happens here is that you have continuity. The function is negative here in the ice, and positive in the water, and it's like this. But one question that arises, how do they match? How is the gradient matching? The function is continuous, but the gradient doesn't need to match. The gradient here is very sharp, here is maybe slow, or it's even sharper. You don't know that. So this is called latent heat. So in the boundary, there's a kinetic energy on the boundary that sort of pushes all the process here, the process of melting. And that kinetic energy is called latent heat. And that latent heat is an extra energy, which actually pushes the ice to be smaller or larger, depending on how you look at it. Okay. So this is a text about just what I told you, which I cannot even read from here. I'm too close to it. Okay, so this is what I just told you about. If you want to read it, just take your time. So there is a mushy region. We usually, in mathematics, we don't see this mushy region most of the time. We call it a narrow one, very smooth. Not necessarily smooth, but at least something very that we can pass quite away. Observe that this mushy region mathematically can have volume, positive volume. It's a region, it's a boundary, but boundaries can have positive volumes, like piano curves and all those things, living curves. Okay. So there's a phase transition here, and so phase transition happens. When phase transition happens, it gives you actually two different type of PDEs, possibly, and across the phase transition, which is the free boundary, there's sort of another PDE, which is of lower degree. So you have a PDE, which is a little bit unusual to think of a PDE on the surface. But of course, that's people can work on that. You already have normal data, normal problem. When you work with normal problem, if this normal derivative of the function is given to you on the boundary, that's a PDE, but not order 2, but order 1. If you work with the Dirichlet problem, you say Laplacian equals something, and u is 0. U is 0, but that's a PDE, but it's of order 0. You can look at that equation as order 0 PDE. So for this is phase transition. What happens is that you have a PDE here, you have another PDE on the boundary, and now you think that the boundary is not even smooth. How can you have a PDE there? So you have to define it very weakly, extremely weak. You have to find what that weak is, so that have a meaning. You cannot take derivatives, so you have to find. So here is the condition that I told you about the jump. So we may have a jump. So the gradient of one side minus the gradient of the other side, they're not equal. If they're equal, it's something like this. If they're not equal, there's a jump of the gradient. And you get that jump is usually a number, positive number, depending on which side you're looking at. So, and in this case, I'm looking at the stationary case, Laplacian. I'm not going to talk about heat equation in general. I'm going to talk about the stationary case, the Laplacian. Most of the cases, all the cases, I think, will be just the Laplacian. There's one or two places I'm talking about it, but okay, there are many other problems. The Hilleshov one that I just showed you experiment, the Muscat problem was actually sort of cheating Muscat, I would call it, and my second with two phases. So Muscat is a two-phase problem, and that is a very extremely hard problem, and still many aspects of it is unsolved problem. Then you can just go on with the Stokes and all that, the Stokes law and all that. So the Hilleshov law, which is the good problem in the sense that it's easier, has also a lot of applications, especially in the lubrication industry. We use it a lot. And of course, thin film production industry.
I wanted to ask a question.
You wanted to ask a question,
Yes,
please?
you showed those experiments.
Yeah.
So when you have those two different liquids,
Yeah.
Isn't it a bit similar like those two bubble problem, double bubble problem?
Double bubble problem? What exactly is that? When you have the tower problems?
Yeah, like means still isoperimetric, but you have two bubbles. Instead of one soap bubble, you have two double bubble.
No, this is not the same. That's a different problem.
Yeah.
Okay.
But still, like the kind of interface is kind of similar. I don't know.
Let me think, since we have good time, we can think about it.
Yeah.
So the double bubble problem is a minimal surface problem.
Yeah, minimal. Yeah,
it's a minimal surface problem.
Yes.
And then when they come together, then there's a flat piece.
Yes.
But here it's not necessarily flat.
Okay.
Over there's a difference.
Because there also it's a free boundary, right?
It's a free boundary.
It's still a free boundary.
It's not a graph.
No.
It's not a graph. It is parametric.
Yes.
So that's the difference. That's the difference here. I don't work in general. I don't see many free boundaries in this aspect that I'm looking at from a parametric point of view.
Okay.
But those who are saying, some of them are, many of them are solved.
Yes.
I think the problem is when you have three bubbles coming and you want to have the angles.
Yes.
Those are the interesting questions. Yeah. I haven't studied this problem. Just that's something to look at. But those are very nice problems. No, but they are not related in that sense. Because the free boundary conditions here, there's a phase transition condition here. I think in those problems, I don't see any phase transition.
No, I think they are just balancing conditions there. So it's natural balancing. Whereas here you may have something depending on those phases.
Yes, exactly. This is very good. I think that sense. I think theoretically you treat them also differently.
Okay, yeah.
Okay, so let us now, I will go slowly through these slides because it has a lot of problem in your mathematics, some of the students. And so what we do, we start with the Hilleshov flow and want to see what happens. So think of the flow. I had for you two plates pushing. Now think that they are not plates, but the picture is like this, that there is an injection. So what I'm doing is I'm injecting. Okay. So I'm injecting liquid at the point where I measure a domain here. So and I call this mu, this set mu. You can always think of mu to be Dirac mass. I guess everybody's familiar with Dirac mass. So think of mu to be Dirac mass. So you're pushing, injecting at one point source, liquid, and this expands. You can think that initially you have already some liquid here, and then you just inject more, and then this will expand, and expand. And this is your initial flow. It's pretty much like the one with two plates. But instead of having two plates, you can think of this one. Both are very similar problems. This is easier to illustrate mathematically. So the question is, how do we write mathematics for this? Okay, but the first thing you ask yourself, what is the rule this boundary is moving? There must be a rule. There must be some physical rule. Okay, and the way we describe it is that there is a Green's function for this. So think of a point source, so there is a Green's function, and we call it Green's potential because there is a measure here in general. That measure could be a nice function. So if you don't like measures, think of a smooth function. If you don't like Dirac mass, think of a function which is like this. That's your Dirac mass, and then if the peak is higher, so this is the Dirac mass. If the peak is higher, the total mass is always 1 in beneath here. If the peak is higher, this is a narrower, then we get closer to the Dirac mass. Okay, but we keep always one volume or area here. So there's always one. So if you don't like this, you can make it flat like this, anything, let's smooth it out. So this the mass is always one. So what happens here is that you're injecting here, for the Dirac mass is here. Approximately Dirac mass. And then this is getting larger. Then you have a Green's function. So call it Green's function. I think I call it G Green or something like that. And the Green's function. And then the Laplacian of the Green's function for this measure is going to be minus E. I'm normalizing it. If you take Green's function, that would be the fundamental solution. That's in dimension 2 is logarithmic. In dimension larger than 2 is x to power 2 minus n with a constant in front of it. So that's the fundamental solution. So the Green's function is like fundamental solution minus the harmonic function, which balances on the boundary, and the Green's function becomes 0. Okay. And the Green's function is 0. So this is in the domain. I'm not specifying D here, but I'm saying in the domain. So this is just general definition of the Green's function on the boundary of the domain. Okay, so this is the Green's function. Green's function. D. Any domain D with respect to the measure or Green's potential. When you go away from Dirac mass to general functions, we call it Green's potential. Okay, so what happens here is, I have to switch to my, thank you. So what happens here is that we're looking for a push. So we're solving this. So the idea is that the system is moving according to the rule that you solve your Green's function at each time. That's the reason that initially I wanted the domain. That's easier to solve the problem, but you don't really need that. So initially you have the domain D0. You start with D0. That's the initial domain I have. And then you solve your problem here. That's a mathematical problem that can be solved either by hand or theoretically prove there is a solution or numerical. So probably the best one is to do the numerical one and then just see the process. We did actually, what we did was exactly the same thing, but we always solved for a measure which is like constant, all the time is constant. So that's different, but very close to this one. So you solve this, and then I am correct, and then I have boundary data which is 0, exactly, at each time. And then I'm saying that my boundary is moving according to the law that the normal speed in the normal direction, because boundaries are moving in the normal direction. They don't move in tangential direction, because nothing happens if they move in tangential direction. If you have a circle and you move it in tangential direction, nothing happens. If you move in the normal direction, it expands. And then the normal derivative of this, here, so you have the normal derivative of the Green's function. You take a minus because normal derivative is pointing inside, the function is larger inside. And then, so you say the minus gradient of g, that's outside. So it's moving outside like this. So here is the total.
He came here. Good job, something. Oh.
So I went in front of this and started. So everyone's okay?
Yeah.
Okay, so put your seatbelts on. So let's go back to the Green's function. So here, the v here is sort of the speed. So there is a total speed, and each point on the boundary moves, and it moves in the direction of the Green's function, gradient of the Green's function, in the opposite of that, of course. Okay. So that's the rule. So you have the Green's function, and that we can always solve numerically, theoretically, or by hand. And you know that the rule is that it moves in this direction, normal direction, with the speed of the normal derivative of the Green's function. Now the question is, how can we find a function that is representing something here that can give us a little bit more? So what I want to do is connect this with the obstacle problem. So what I do is I do a Biot transformation. I think it's called and then what you do is that you think of this, that the domain is expanding, getting larger and larger, and you put an axis, call it t-axis. At each time you have a larger domain. So the domain is like this, getting larger and larger. And what you want to do is to compute the total, let's not call it mass, but pressure from time 0 to here. And if your initial domain, in the initial domain you see that you will have sort of larger values if you integrate the total mass or the total pressure. And if you're outside, it will be smaller because you're just having these small pieces. And you're completely on the boundary, then there is nothing, it will be 0. So if I integrate the Green's function from 0 to t, it means that it will have different values depending on where I am. And I will have a picture which is like this. So this is the initial domain. Let me make it smaller. So this is the initial domain, and then it's becoming larger and larger. Time goes, it's larger and larger. And then I'm integrating from this. The function is 0 till here, and then there is a mass. The function is 0, and then there is a mass here, and then the boundary is always 0. So this function I'm defining is always 0 on the boundary of dt. That's the good news. It's always positive inside dt. And of course, the more inside you go, you get larger values. So if you start here, see you have more masses here to add up. And well, that's a function. Works perfect. So the question is, what is the Laplacian of this function? You can compute it, and this is what you come up with. I will do a little bit drill with this. So if you compute it, it will be so this is g of dt or I of dt. That's the characteristic function. So this is 1 on dt, and it's 0 otherwise on dt constant. So the function which is 1 and 0. So it will be 1, Laplacian will be 1, and the whole domain will be minus the characteristic function of d0, so it will be minus 1 on this one, and then minus t of mu. Because as time goes, it will accumulate more measure here, so this is what we get. Okay, why do we do this at all? What is interesting with changing the whole thing? Well, the interesting thing is that if you have these domains that are moving along, you can probably compute this Green's function. But the first question is, how do we prove generally existence of such a problem? Mathematically, we want to prove existence. So how do we do that? And in order to do that, you need to have a variational model, or have a model when you have everything is smooth. Because I'm talking about normal derivative of the Green's function. If I don't know what even the boundary is, I don't even know what my domain is, how can I talk about the normal derivative? How can I talk about the normal of it? So my question going back here is already strange. I'm saying that it's moving in the normal direction. But does the boundary have a normal? The boundary might be something like this. So what happens then? So the question would be, is this problem meaningful? Can I do a setup for this? And I'm saying, yes, we can probably do that if we can solve it from a PE perspective by rewriting it, doing a new model, and then solving that, and then saying that this model is actually compared with the original model, it solves the original model. So you see the way back is also the problem. You have to say that this really is solving the problem. So what you do is you do this transformation, and then you integral from 0 to t, and then the function becomes smoother, it becomes nicer. And in this way, when you write it like this, it allows you to solve the problem, but possibly if you know the techniques. And the question is, this is given, the measure is given, the initial Dirac mass or whatever we have is given, t is just a value, t, and then d0 is given, that was the initial domain we started with. So this information is given to you. This is not given to you, and this is not given to you. So what you're saying is, can we solve this problem when the two last ones are given? And the answer is yes, you can solve it. Actually, there's a technique that solves this problem and gives you an exact solution. And once you do that, you will probably want to go back and then take the derivative of this function u in time. The function is sort of time dependent because there's a time. It's not a heat equation, it's a spatial equation, but it's time dependent. For different, well, time is really a parameter, it's not really time, it's a parameter. Okay, so it depends on the parameter t. Take the derivative of this in t. This will be the measure, so you're getting back your Green's function sort of. This will be 0, characteristic function, there is no t here. This will be something, you don't know what it is. It will be 0 outside, it will be 0 inside because it's 1. On the boundary, something can happen because the boundary is moving with t. So the derivative of this on the boundary will give you something. We don't know what it is at this stage. So it will be minus measure 0 and something on the boundary. And if you look at the Green's function we have, it looks like that because Laplacian of this will be the measure plus maybe something on the boundary. If I'm not talking about the boundary, this is perfect. This seems to be the Green's function. And observe that this is, you have to probably, well, not put very much there because that's enough that the function is 0 on the boundary. I think the derivative of this is 0 on the boundary, that would be exactly by uniqueness of the Green's function. Okay? So let's see what we have here. Oh, I'm going too fast. Why is it going in one way? Okay. I'm not so good at this. I'm going back on. Okay. So.
Yeah.
So let us look at so f here is the fundamental solution to the Laplacian, whatever dimension you are. So I'm looking at Laplacian of f being the arc mass. Okay. If you're not used to fundamental solution, here is the fundamental solution. So logarithm of x, it should be minus 1 here, and there should be a constant called C2, which is normalizing. Otherwise, you get a constant in front of it. If you take Laplacian of this, you will get actually the arc mass. And then in dimension larger than 2, you have this one, C, and so this is the fundamental, and 2 minuses. 2 minuses, it will be the fundamental solution. So Laplacian of this is that the arc mass, if Cn is picked up correctly as C2, and then you get exactly what you want. So what I do, if I take the fundamental solution, this is convolution. So you're convoluting it with the right-hand side. Okay, so this is the characteristic function minus t of mu, and then you take the convolution of this. You see, I skipped that d0 here. There is no d0 here. I skipped that for the moment. I will add it on later. So if I'm looking at this function v, which actually is not unnatural, because if I'm thinking of my solution to PDE, I'm thinking how can that be built up? And if I'm guessing it right, then I'm sort of saying that, okay, it should be built up like this. Because Green's functions are coming through fundamental solution convoluted with the mass you have. And that gives you actually, the Laplacian of that will give you the mass back. Okay, think of your ODE class, if you remember your differential equation class. There you always have this fundamental solution through algebra. You have the main matrix equations. That fundamental solution tells you that if you convolve it with any function, it will give you back the function by applying the PDE to it. That's it. That's what we're doing here. Nothing else. So what I'm doing, I'm going to take the derivative of this function, see what happens. You see, in the Green's function I have no d0, basically. That's the reason I'm sort of trying to get that Green's function back somehow. And then there is no dz, so I don't involve that dz. I'm taking the derivative of this function, so I go back here. Well, f doesn't have any t in it, so let's say formally we can just go inside and take the derivative. You have to mathematically verify this, but let's say that we're good enough to accept that this we can do. So we go inside and take the derivatives. The derivative of this one, the t disappears. The derivative of this one, I'm writing it like this. And why is that? So take the derivative of the characteristic function of a domain. The only thing you will get is 0, 0, and something on the boundary. Because the function is 1 here, the derivative is 0. It doesn't, inside doesn't move, only boundary is moving. And outside doesn't move, only boundary of the outside is moving. So the derivative will be 0, 0, and then something on the boundary. And then something I'm claiming is going to be this. It's going to be the surface measure if it's smooth. I'm saying that I'm dealing with smooth cases. I just want to verify that this model is a correct model. So what you're going to get is a Dirac mass on the boundary. That's the surface measure. That's the surface measure. And then you get something v. And that v is exactly the speed how it's changed. Because you're taking the derivative. So think of characteristic function of dt is getting larger, and then you put your axis t. It becomes larger. So you're taking the derivative in this direction. Okay, you take the derivative of this function, which is a graph, something like this. You don't know what it looks like, but you're taking the derivative in this direction. So you get really that only on the boundary, and then the speed of this, and the speed of this is exactly the tangent here of this. So that's exactly what you get. So you can always see one dimensional. That's easy. That's anyway how I do it when I'm working with it. So v is of course the speed, and we said the speed is what? We said already dictated this. So at the beginning we said v speed is this one. Move with that speed. So just put it back, and then I will see that the fundamental solution convoluted with this is going to, because if you take the whole thing here, you see that's going to be Laplacian. This might be a little bit unfamiliar. So if you take Laplacian of the Green's function, we said it's going to be a measure if you're inside the domain. But what happens outside is 0? What happens on the boundary? So there is another measure of the boundary, plus something on the boundary of it. Because the function is not smooth on the boundary, there's a jump. You take the Laplacian, something happens.
A darker pen. The red
Oh,
one.
yeah, red
the
one.
red one, yeah.
Something on the boundary of dt. And that something on the boundary of dt is actually normal derivative of the Green's function. You have to go positive, yes. And then the surface measure. The surface measure is formal notation. It tells you that this is only on the boundary. So that's what we're going to get. That we're going to get, what do I have minus here? Oh, this is, okay, so Laplacian of gt is minus, v was, yeah, okay, this was the speed, so
Yeah.
we're going to get this, I think it should be plus.
Minus.
Okay, so let me accept it, I cannot think right now. And then you're going to get your Green's function back. So what it says is that the derivative of this is exactly the Green's function. So if you put from the beginning your function v like this, you actually get back your Green's function, and you see that v is sort of related to u. There is just one difference with this characteristic of v0 that I'm not taking u. Okay, and this is now negative. That's a good information to have. It means that the Green's function is going to be non-negative. And we're assuming, of course, everything is smooth. But if you go back to your function u, which was, by definition, integral of g, and take the derivative of that, go back to u, take the derivative of that, you're going to get back g. So it means u and v are the same, almost the same, up to a constant, because the derivatives are the same. The derivative in t. So it means u is v minus something, not constant in t, a constant in t, but not constant in x. And we don't know what it is. And we get cx. So what I do, I just go back and look at what happens at the time 0. For time 0, I'm going to get f is exactly fundamental solution convoluted with characteristic function of dt at time 0 minus time measured. But time 0, so that measure is gone. So I get vx0 is exactly this one. And I also have ux0 is 0. This is by definition. Integral from 0 to 0 is 0. So what we have is that this is 0, so c has to be equal to b. And you have it. And v at time 0. But v at time 0 is exactly it. So cx is, so you see we get back v0 here again. So what I claimed from the beginning is exactly correct. So this should be the solution. Okay. So this tells us what? So this tells us that oh my God. So this tells us that if we start with this process of solving the initial problem, which at the beginning is very vague, because it's talking about moving the normal direction, speed in the normal direction, and we don't even have a normal at the beginning, we don't know if we had it. The question is whether we can solve this problem. And then what I'm saying is, what people have told us earlier, I'm just repeating it, is that we can actually remodel this, reformulate this in terms of a function which is more solid. And that function is the u function, u of xt. That function has a very good character, because I'm saying that that function has a Laplacian, which has a right inside, is the characteristic function, and etc. And that means that you will learn soon that that PD is solvable, actually. You can solve that PD. There is no sequence of domains anymore. There is a problem with parameters. So each time t gives you a solution. It's not so vague. I'm saying that it moves like this. I'm not talking about moving. I'm saying solve this problem at each time. That's it. But we really don't have time in the sense of moving or something. You have a parameter. You can solve the problem. Solving and then going back. And we sort of went back here. So this is actually the original problem. So what we will be doing is actually solving the problems related to the function u. It becomes now an important class of problem to solve. So what we're doing with time-wise?
Half an hour.
Okay, so this is a short flow, and let me relate this to, do you remember your statistics course or stochastics course? Probability course?
Probability, yes.
How many of you are taking a probability course?
It's a compulsory course. They all took.
Everybody has taken.
Except
Okay. So I'm not bothering you with this, but let me just tell you a little bit how you can actually interpret this in the stochastic versions of this. So if you think of a Brownian motion, okay, so we are familiar with Brownian motion. So it's a motion of particles, random motion of particles. Actually, Brownian motion is coming from, the name Brown is Robert Brown, in 1827 or something. He's a Buddhist. So he started looking at grains, pollen grains on the water, and they were sort of jumping. Pollen grains were jumping, and they realized that this must be some mechanism that he doesn't see from inside. So something from inside is coming, and that things are moving on the surface. So these grains are moving, pollen grains are moving. And the question was whether this erratic moving, the question is whether there's a control in that. And then much later on, I don't know the history, but almost 100 years later, in 1903 or 05, I guess, Einstein gave some good explanation of this mathematically. I think before that, somebody else did, some physicists did it. But so this is Einstein put the mathematical theory behind this, that this is really motion that you can model mathematically. The physical reason for that is that all molecules if you have a molecule, the atoms are sort of very strangely going around it, and they're bombarding the inside molecule, the walls of the molecule, and then they come back. If there is an imbalance of bombarding one side a little bit more than the other side, then it will move. That's basically the physical nature of Brownian motion. And then when people realized, and Einstein realized, that we cannot go at that level and study it, so you have to average it out. And averaging out is something that people do today as well. So they average out this Brownian motion, or this random walk, and then they come up. So averaging out would mean basically expected values. So here it is. So your average comes out basically. So this is x is a Brownian motion basically, and then what you, instead of each x I had, you go back and you put x of s, and s is the time. At each time this particle is moving randomly like this. So you start initially at your measure, so each measure point has a particle, and then it's one to move out. And then, of course, our problem is related to, when it's moving, related to optimizing something, or maximizing, or minimizing something. And then it's exactly this problem. If you take expected value of tau is it's called the stopping time. Stopping time, let me not go into that. Stopping time is a kind of random variable whose level sets are measurable sets, basically. Are measurable sets in the sense of probability space that you will see only related to the expected value. When you take expected value, there's a probability space. So what you have is that this is a stopping time, and that stopping time is always a measurable function, basically. And it's the real value, so you can put it here. But for each x, you can put it here. It's a real value, x of s. And then you integrate the whole thing, and you can actually, through Feynman CAG models, prove that this is exactly the model you're looking for. So you can actually look at the problem from this setting, probabilistic setting. I have a small paper on this from 2005, I think, about the translation of the model in this. So you take the supremo of this. Just think of the theta is 0. You can always take theta to be 0. That's one of the optimal stopping times as a random variable. If theta is 0, this is 0, this is 0, the function is 0. So that already tells you that this function is non-negative. Not this function is non-negative when it comes to supremo. And if you want to do, it's a very nice calculus to do, a detailed calculus, to take the derivative of this Laplacian of this, and you'll see that you're really getting back your whatever you have. And it's a calculus at the level of actually calculus. It's called beta calculus. But beta calculus has one more thing in it, and the only difference is that in beta calculus you have the Brownian motion. I'm writing with x here, so dx. If you take the power of 2, that actually the time. So that's the difference. That's the only difference. It's not bad to read about it, just as a general knowledge. I have some lecture notes on this. It's a 2 hours lecture notes I have on my webpage. If you want to look at it, you can actually handwritten notes, basically. It's a little bit heavy for 2 hours, but it might need a few days. I need 2 months to write it because it's covered everything from the beginning to the PDEs, how we get to PDE. I had to do it all in 2 hours. So, okay. So another way of seeing this is looking at so I'm just exposing you to a different type of mathematical radiations here, so you'll see a lot of problems, but we will soon get into each one of them and try to look at it more carefully and rigorously. So another way of looking at this is the variational model. This is the reason we went away from the Green's function formulation to something which is more solid, and that's exactly this type of models. So what you say is that, so forget about this. So Laplacian we recognize, psi is a function, let's say, we recognize it. It's a function, it's given to us, psi is given to us, and g is also given to us in boundary values. What I'm looking for is, I'm taking minimum of these two have to be 0. So first of all, if minimum is 0, it means that we are looking for, they both have to be non-negative. If minimum is 0, it means both are non-negative. So it already tells me that u is minus psi is non-negative. So u is larger than psi. That's one information. If u is strictly larger than psi, it means u minus psi is strictly positive. So this cannot be 0 if I choose this one. So this one has to be 0. So if either you are larger than or equal to, so it means you're attaching to your obstacle psi, or you're strictly positive, strictly larger. When you're strictly larger, the u is strictly larger, then this has to be 0, so it has to be harmonic. So either harmonic, or you're attaching to your obstacle. That's a model, that's a formula for you. It's called, this is the most basic obstacle problem. There's the most simple form you can actually model. We're going to see a lot of this in variations. So we're going to develop this to different type of rewriting and then solving. So the other problem I just told you is exactly this one. Actually, I can rewrite it in a stochastic way of looking at it. So let me go further. So here is a picture for you. So you have an obstacle. So this is the obstacle here. And then you have a membrane. So think of somebody who wants to have a hat. And then there is a boundary given, a reach given. So it's a wire here, and you have a garment attached to this wire. And somebody comes in beneath and puts its head, and then it will be a picture of the head. And then some places will be free. And this body part is basically the obstacle. And then where it's attached, that's exactly equality. And when it's away, that's free. And when it's away, this piece here should be harmonic, in the sense that the graph should be harmonic. Laplacian of that is 0. Okay, I again went back. Okay, so let me, I think the next one is the last one. So let me look at the model. Anybody who likes financial mathematics or who's planning to like it? Nobody is in financial mathematics here. Nobody wants to work in the banks. Anybody who likes money? Good. Okay. So, yeah, I mean, you like to have it, but you don't necessarily need to like it. Okay, so if you start with, do we know what option is? The financial instrument option? So you want to, if you go to the bank, anybody who has looked at the stock market? Nobody? Oops. Shares, stocks. Let's say there is a company here, and that company sells shares, stocks. You go and buy the stock, and the stock goes up and down. So that's the value. I will call it S, the value of the stock. But now think like this, that you go to the bank, so I don't want the stock, but I want the possibility of buying it in the future. So let's say the stock you want, so let me mention Ericsson, that's a Swedish company. So you have to come to Sweden. Why? So you go to the bank and say you want to buy the Ericsson share. The price today is like, let's say $30 or whatever. And then you say, well, I want to buy this next year, next summer, this date. But I want to buy it for a certain value, like 15 kroner. It's 20 today, but I want to buy it cheaper. Or let's say 25 kroner. I know that it's going to rise, so I will buy it then. And then if it rises more than I'm predicting, then I will have, because I'm fixing the value today for the future. I'm saying I will buy it for 25, but I'm expecting it to be 30 next year. Okay, bank doesn't know it. The bank says, okay, if you want that opportunity, okay, if you want that opportunity to buy the Ericsson for this price, 25, we will give you that opportunity. We will write a contract with you, but you have to pay something to us. Because if the price is 30, we are going to sell to you for 25. So you're going to win, we're going to lose. So somehow we have to compensate this. So give us some money now, and in the future, we will give you this contract that we can exercise in the future. That's called the European call option. So you give some money today, upfront, and then in the future you will get your stock with the price that you and your company or your bank have decided upon for exactly the amount you're giving today. So that's called European call option. You cannot go outside this contract, and the last day you have to really do the business. If it's lower, then you're going to lose. If it's upper, you're going to win money. Now, there's another alternative. It's called American option. You say, I want also one further thing in this contract, that I can get out of this contract whenever I want to. I can sell my option whenever I want to. Or it's called exercise. You exercise whenever you want to before that date. Okay? But that should have a larger value. That option, that contract is a larger value. So here it is, V, and that is related to an obstacle problem because it has to be above certain values. It can never be below the final value. Because below it means I'm always making money. So what you do is you put the value in V for the value of the option. S is the value of the stock. N is the number of the stock you're buying. It doesn't need to be an integer value. It can be a real value, because mathematically you have to work with it, so we assume that it's a real value. So what you have is a portfolio. That portfolio has one option. We don't know what the value is. We're trying to find it. So we're putting up a model to find it. And then the number of stocks in negative. Okay, so it's called long. It means that you actually can do the reverse to bank. Bank doesn't do it, but you can do it to other people that sell the option, buy option, sell option. Okay, so when you're buying the option, it's called long. You go long to keep the contract you have. You go short asset. You can actually sell an asset even without having it. But when it's time to exercise, you have to pay it. So nowadays you can do a lot. And you can do that for the undergraduate as well. So what you have is V minus MS, that's the portfolio. That's an amount of money here. So I know the value of the stock today, but in the future I don't know. This is given constant m, I know it, and I can change it. And that's very important, because I change it in the way so that we get rid of the stochastic process. Because stock's value follow a kind of Brownian motion, a combination of Brownian motion with time-dependent interest rate. So you take the derivative of this, nothing happens, it's just a derivative, divide it like this. And you use the Ito's formula very soon. So this is the Brownian motion, W is the Brownian motion, and this is the interest rate here. Sigma is the volatility, so radically the value changes, so this usually is coming from empirical values. You don't know this that much exactly, so you just sort of guess it. So the banks always guess that through the history. So I'm jumping ahead here. So if you use the Ito's formula, you can actually put the value of the pi here, and you can actually compute it. Compute it with, you take the first derivatives. First derivatives usually you use second derivatives of the v in SS, because first derivatives in the second derivative, first derivatives in t is the second derivatives of dx, so the w. And that gives you actually this guy here back. So it will be, so from an ODE flow of x, the value of the stock follows an ODE. It gives you a second order PDE for the value of the option. So this is what you get. If you want to learn more about this, I have some lecture notes about it, but if you're not, so you can skip it. So what you get is an equation, and you also know that V always has to stay larger than psi. Psi is the final value. It always has to stay, otherwise you always make money without being bothered. So it's called free lunch usually. And then this is a differential inequality. So there are two important ingredients. V is larger than this, and the PD is less than or equal to 0 in weak sense. We don't know what this means at this moment, because we're not familiar with weak senses. We don't know even that V is differential. So you realize the difficulties here. But we're trying just to model it, so it means that we think of everything is smooth. When we model, everything is smooth. And just realize that this is correct model or not. Okay, you need one more ingredient. Because think of functions that are larger than psi, so this is the psi, functions that are larger than that, and they are super solutions to this. The best way to think of this is a concave function. Because if you forget about this, forget about this part, forget about these constants, what you have is the second derivative is less than or equal to 0. And then a lot of disturbances around it. So it's like a concave function. Think of a concave function over an obstacle, over psi. Of course I can give something like this, that's a solution. I can give something much larger, that's a solution. So it means that you have a bunch of solutions. So when you go to the bank has only this information, and it will tell you, okay, I will solve this problem, and just by hand I can draw the solution. This is the price for you. And then the next guy, the next bank, will say, oh, that's really too much, I can go lower, theoretically still make money. And then the third bank will say, oh, you're not low enough. Theoretically, you're making money, but theoretically you can make money even you're lower. And then people just go on. What you do is you take the smallest possible value. Because if it satisfies this, you make money. I mean, let's say bank doesn't lose money. Okay, theoretically, bank doesn't want to lose money. They don't want to make money in the sense they want the margins, they want the transaction costs. Okay, so the extra money they want. Not really make money with this, because there's another one who will write exactly the opposite of this, because they don't want to jeopardize it. So they write this one with you, the opposite with another one, so it goes like 0, 0. But everybody has to pay some money, a little bit more extra, and they will make that little bit margins. So if you look at this, you say the bank can always make huge money if you just choose randomly the picture. This is the graph. But the next bank will make it smaller and smaller, and then the last piece of the PD is to take the smallest possible solution. That would be theoretically the right price. Okay? I'm backing into something. So theoretically, you take the smallest price, the smallest value for the, it will be this ingredient, this one, and the smallest one. That's the solution to the PD we just wrote, the minimum of the two things. They're very much related to this. That was Laplacian, here is the parabolic PD. So this is the financial situation, time-dependent PDs, which is an obstacle problem. So I think I will finish with this one. So another problem, which is actually quite pretty nice, is that it's related to random walks. And think of the following. I will not need to wait this, I will explain it to you. So think of this is a smash sum here. So think of two domains that are overlapping partly. Okay? So the picture is like this. So you start with two domains, and then there the lattice is Z2. So it means so these are all points here. So it's that Z2 lattice. And now those points that are inside, they are double because they're overlapping. So each domain is represented by lattice points. Okay, and then when they overlap, at each lattice point there are two brackets, there are 2 points. So it's double. So the rule is this, that whenever it's double, one moves out. So you have 2 here, so 1 goes out. So you start walking randomly. So you randomly walk until you hit the first point, which is outside the beginning. And then you stay here. So this guy here walks, and then he stays here outside. The next guy here walks, and then stays here. And then you do this, and then eventually you will have a picture like this. So when you have a picture like this, it means that at every spot there is only one person sitting. Believe it or not, this is actually an obstacle problem. Exactly the model I described to you with the original model. So this is, if you take the intersection, that measure I had, that's the measure, exactly the double measure. The measure I have is the double points here. And the initial domain, I have D0 as the union of the two of them. And dt is the time later on, is exactly when you walked out and completely occupied. And now we can think that more measures are coming, so we can think that this is Z2, you're working, and now we can think of epsilon times Z2. The mesh is much smaller, so it means that really you have a bunch of points here. And the lattice epsilon times Z2. Epsilon goes to 0. The number of the points here is becoming larger, and the domain is becoming more pictorial. You can see that. And that eventually what happens is will be a very nice and fine shape that I have it here. Not here.
Here from intersection, when it moves out randomly, or?
Yes, it's random movement. You don't have any control of it. It's random walk. It's 1/4 of possibilities in each direction. Just go here, it's occupied, you move it randomly until it's not occupied, you sit there. First time it's not occupied, you just sit there. And the next guy it starts to move. And here, so we started with 2 boxes like this. In the middle we have 2 points. And then You move out, and this is the picture. This is just a computer program. And this is exactly the obstacle problem, which you can write like this. Okay, this was it. Oh, anyway, it's the PDE that I just wrote for you, so you're going to get that. And this is the last model. So I think I'll stop here if you have questions or so. So these are the models we're gonna take, and I will expand on them a little bit further. Okay. Good. Thank you. So it took me 1 hour and 30 minutes to do this. Yeah. I went fast.
You went fast.
Did I went
No,
fast?
I think
Was
it's
it fast?
fine.
It's fine? Okay. So how do we do that?
Lunchtime from 12:30 to 1:30.
Okay.
And 1:30. So lunch is outside. I hope we see you. Very first day. You're not going to sit here? No? Yeah. Can you? What is it?